Section 7.3 on trigonometric substitution. So the point of this section, well, let's compare it and contrast it with the previous section. The previous section on trigonometric integrals, there were trig functions explicitly in the integrals that we had to evaluate. In this section, we won't explicitly see any trig functions in the integrals that we need to evaluate, but we'll do some substitution to introduce trig functions and inverse trig functions into them. So, when would we use trig substitution? You'd use it if you need to integrate expressions involving one of the following three expressions. Sometimes you'll have square root of a squared minus x squared. Sometimes you'll have square root of a squared plus x squared. And sometimes you'll have square root of x squared minus a squared. And here, in each one of these, so x is the variable that we'd be integrating over, a we would be thinking of a fixed constant. So really the thing that you're looking for, if you're not looking explicitly for an a in most cases, you might be looking for, if you see something that looks like 16 minus x squared, well, that would be 4 squared minus x squared, and so that would fit this first type. And so there's different things that we do. There's different substitutions we make in each one of these three cases. So what I want to do right now is go over the substitutions that you'd make in each of these cases. And in each one, we are going to resort to drawing. So think back to when we work with like trig function, inverse trig functions. It's usually important for us to draw these triangles here, these right triangles that help us quickly figure out what's going on. So what do I mean by that? In this first case, if we see something that is square root of a squared minus x squared, the thing that we should know, the thing that we should try, is that we'd want to try x is equal to a times sine theta, which is equivalent to, I'm just going to rewrite this as sine theta is equal to x over a. And in this case then, if we substitute in x is equal to a sine theta, dx then is equal to a cosine theta d theta. That's the substitution that we'd want to do. Let's go ahead and fill in the sides of this triangle now. So, and then we'll see why this is a good choice to deal with things of the form square root of a squared minus x squared. So if sine theta, let's say that angle right there is theta. So sine theta is x over a. So here is a right triangle with sine of theta is equal to x over a. And if you think about what the other leg here has to be, by the Pythagorean theorem, the length here plus x squared is equal to a squared, and so solving that means that side length there is exactly equal to square root of a squared minus x squared, which is the quantity that we wanted to deal with in the first place. And so a little bit of thought will show us that this tells us that the square root of a squared minus x squared is equal to a cosine theta. You can also get that, let me go to a new page for this. You can also get that just by substituting in if we have square root of a squared minus x squared, and we substitute in x is equal to a sine theta, we end up with a squared minus a squared sine squared theta. If we're assuming a is positive here, we can pull out that factor of the a squared outside. A times the square root of 1 minus sine squared theta. And of course, that is going to be square root of cosine squared theta. And again, if we're assuming cosine theta is positive, this just becomes a cosine theta. So that's what's going on in this first case. In the second case, the square root of a squared plus x squared, it's a different substitution that we need to do. It will be x is equal to a times tangent theta, which that's equivalent to tangent theta is equal to x over a. And so now we want to fill in a right triangle where here is theta. And so we do x here and a here. We've got the tangent of theta is exactly x over a as desired. And then once again, Pythagorean theorem will say this right here is the square root of a squared plus x squared, which is exactly the quantity that we were looking for up here. So we can fill in the rest of the stuff. I guess I could have done this earlier. If x is a tangent theta, dx is a secant squared theta d theta. And then finally, crunching things out here, square root of a squared plus x squared, this ends up as a times secant theta. So the way to kind of see that is secant theta is 1 over cosine theta. So 1 over cosine theta would be square root x squared, a squared plus x squared divided by a. Multiplying by a produces this desired relation. Our third case, square root of x squared minus a squared. So note the difference here. Order matters. This would be square root of 16 minus x squared. This one would be square root of x squared minus 16, would be the sort of things that we're looking for. And the substitution to make over here would be x is equal to a times secant theta, which ends up as equivalent to cosine theta is equal to a over x. And dx is a times, the derivative of secant theta is secant theta tangent theta, and the d theta there. When we fill in, one more time, fill in the sides of our triangle here, cosine theta is a over x. So we can label that as a, and that as x. And so then this final side is exactly what we want, square root of x squared minus a squared. That's this up here. And to finish this off then, we see that tangent theta is this divided by this, square root of x squared minus a squared divided by a. So square root of x squared minus a squared multiplied by that a is a times tangent theta. So these are all the substitutions that we'll want to do. If you see something with a square root of a squared minus x squared, you should think about substituting in x is equal to a sine theta. If you see square root of a squared plus x squared, think about x is equal to a tangent theta. When you see a square root of x squared minus a squared, think about x is equal to a secant theta. So let's call it wraps on this video. In future videos in this section, we'll actually use these formulas.